Today we're going to be considering question 4 on linear algebra from Gunning's An Introduction to Analysis. It reads as follows. If A is an m by n matrix over field F, should the vector space V consisting of those vectors x within f to the n such that ax equals 0 has dimension at least n minus m. Find an example in which n is greater than m and the dimension of V is strictly greater than n minus m. We'll first note that since A is an m by n matrix over field F, we see that it represents linear transformation from f to the n to f to the m. And we also see, and let's call it linear transformation t. And we also know that the set of this vector space V is simply the null space or the kernel of this transformation t. Therefore, since we have all these interesting facts, let's consider the rank nullity theorem, which says that the dimension of the domain is equal to the dimension of the kernel, which we'll call the nullity, plus the rank, or the dimension of the image of the space. And we've already proved this as a result of our, we've already proved this by considering T, the natural mapping T that makes the image of T isomorphic to the image of the output space. In particular, that if you take T and quotient it by its kernel, you get another map that is that naturally relates the image and the image of T and the output space. With this, we'll note that this left-hand side evaluates to n. We see that n is equal to the nullity of T. And let's call the rank of T the dimension of the image equal to R. We'll then note, there should be a plus sign. We'll then note that since T is being put into f to the m, we can put a bound on the rank, namely that the dimension of the image, or our rank, is less than or equal to the dimension of the output space. It's equal to m. So if we rewrite this, we get n minus r. I'm sorry, let me leave this like this. This nullity of T plus R is less than or equal to the nullity of T plus M, since R is less than or equal to M, plus M. And if we subtract this M over to the left side, we're left with N minus M is less than or equal to the nullity of T. This proves our first statement. Some additional notes we can have is that note we're considering T, but we're given the m by n matrix A, but every m by n matrix A uniquely specifies the transformation T. So if this is true for the transformation, it'll be true for the matrix, in the sense that when you ask the question, what is the dimension of V, it's asking what is the dimension of this space, but this space is the same as a set of all vectors such that Tx vector is equal to 0 vector. Finally, let's continue with an example. We're going to find an example where n is greater than m, so let's use a very easy example, which is R3. And we're having our transformation R3 go to R2, and this is represented by some transformation T. And we need to show that the dimension of V, which is the null space of our mapping, is strictly greater than n minus m. So in this case, n minus m is equal to 1, so we simply need the dimension of V to be greater than 1. So consider all these vectors that get sent to 0. Well, a very easy example of a map that sends, that'll have dimension of the null space being greater than just 1 is the 0 map. So if we actually consider the matrix represented by A, it goes from R3 to R2. So if you fill it in with all zeros, we see that every vector in R3 is sent to 0. Therefore, the dimension of R3 is the dimension of the null space is equal to 3. So dimension of V is equal to 3, which is greater than 1. With that, we're done. Thank you for watching.